So they also, thank you. Continue, Sumit.
Thank you. So the agenda, what we have prepared for today is basically we will be introducing some of the things related to the CST. And other than that, we will be going for some of the design methodologies for antennas and antenna array. Then the significance of human exposure analysis. And Jagasar suggested that we needed to include something about the wearable antennas. So I have kept some slides, but I will be showing that on the tool as well. Then we will be focusing on the filter analysis as well, because what I believe is antenna is a passive structure, but over the years, this passive application of the antenna is not obsolete, but active antennas are getting more attention, especially on the 5G antenna or anything related to 5G. Basically, the preferred choice is active antennas. So active antennas are equipped with the passive structure of the antenna along with the other components as well. So whatever we are trying to show you that it's a mixture of everything that is possible with the solution. And we will have some session for demonstration. I will show you some of the models that we already prepared over here. And we can have a question answer session as well. So when you ask questions, we will get more input from you that what are the demands in the academic spectrum and research applications. Also, we will be sharing our knowledge over to you, even you are using any kind of tool, how we can able to do the simulation or how to do the design and aspects, and in the industrial scale. Like Srinivas has introduced us, we are a global multinational company, headquarters in USA. We have a team of scientists and engineers who work on different kind of domains, not only electromagnetics. We have our expertise in the structural mechanics, even data analytics, etc. Also, we are part of Dassault Systems, and we also provide you the engineering services, training, and other software sales and supports, even including the automation, customization of the solutions, etc.
Sumit, so sir.
Have a, yes, sir.
Sumit, somewhat disturbance is coming from your side, sir. Resound is coming. Can you check, sir? If you don't mind.
Yeah, let me check. Yeah, sure. Are we getting the same noise?
No, sir. No, now it is okay, sir.
It is better, Sumit. Yes, you can go ahead. Yes.
So when I'm talking about the CST is part of Dassault Simulia group. So including the Simulia, we have a different product for different kind of applications. Okay. So CST is our prime tool, which is used for the RF and microwave application. And we also have the antenna magus. This antenna magus is constructed of an antenna library and including the material library, etc. It contains almost more than 400 plus different kind of antennas. You can use that antennas for the synthesis, and you can later export into CST for optimization if it required. And also antenna magus can be used for the design of the domes for the different kind of antennas. Or also you can use for the synthesis of antenna array. So that is one of the important tool, and it is given to all the academic institution as well. Opera is, on the other hand, it's a low frequency electromagnetics tool which can be used dedicatedly for the applications like motor design on different kind of low frequency things. S3D, Spark 3D, basically they are used for the waveguide kind of components. But generally it is used in the industries. If your research is coming into the waveguide or high power waveguide kind of structures, then you will be having interest in this kind of tools, etc. Now coming to the technical capabilities, I'm not going in detail. So what are the things you can do if you have a one standard license of CST? That is what we are going to discuss. Okay. So CST, like you can see a pie diagram where you have a wheel, you have a different kind of options are here. One thing is the microwave and RF optical. So when I'm talking, whatever I'm going to show you, it's all coming under one standard license. Okay. One thing is microwave, RF, and optical. In microwave, RF, and optical, what are the things you can do? One thing is antenna design, antenna array designs, etc. Then circuit and components. As I mentioned before, passive antennas are not the area of interest nowadays. More than that, active antennas are getting more attention. So every time when you consider the active antenna, it is having the passive structure along with the circuit and amplifiers components are there. So we have the option to add the circuitry along with the antenna here. So that is circuit and components coming in the picture. I will show you that what are the things are there. Then radar cross section, obviously it is a defense aerospace application, which can be used not only for the monostatic and bistatic RCS. You can also see the field of view or ISAR, or if you want to see the hotspot kind of thing, you can do with the radar cross section block. Then biomedical exposure SAR, when you're talking about the base station antenna array or something like big antenna arrays you are considering, you may be either you want to comply with IC, NRP, International Council for Non-Ionization Radio Protection standards, or ARPA Mensa, that kind of standards will be there. Or normal FCC standards, including the specific absorption rate kind of applications you may deal with. So that is also part of the interest. Then optical application, that is one of the biggest thing. I think that most of us, we are not much experienced, because I'm also coming in the EM background, but I have also studied about the optical electronics applications, but I didn't much work on that thing. But nowadays, people are getting more interested in the optical things, including the even suppose the design of plasma gigabit structures, or if you are dealing with the solar cells, the renewable energy is one of the most important scenario now. So people are all discussing about so many companies are there in Hyderabad, Tamil Nadu, etc., related to the design and manufacturing of the solar panels, etc. So solar cell analysis is one of the important things. That is not doing like conventional microwave tools, but CST have the capability to address the optical applications. Then periodic structures are nothing but the design of frequencies, relative surfaces, or any kind of analysis kind of thing. So you are already familiar with this kind of applications. So another block is the electronic design application, or the pure electronics block. Unfortunately, in academics, none of us is studying much on the basic circuit problems. We will do some design of the circuit, and most of the times in our career projects, or in the chapters, we generally study about ICs or different kind of circuits, etc. And for our minor or major project, we'll be doing some circuit designs. We use some softwares, and none of us is much care about what exactly happening with that circuit. And that is the most interesting part, or most demanding part in the industry. Even in India, you say that even 65% of the jobs are related to the electronic design application domain. If you studied in microwave and you are searching for only for the antenna job, that is not possible. But at the same time, electronic design application, if you're looking into that thing, you will get an job easily. Because every company who have a product related to electronics, they have to do the analysis of the PCB, not just the design of the PCB. You have to combine the PCB with a several kind of testing. One thing is signal integrity analysis. Is not a part of interest of this session, but however, I tell you that signal integrity, how much it is important, which is going to tell you about the crosstalk cost because of the trace mismatches, etc. Basically, you are studying the interdisciplinary references. That is what the area of interest for the engineers. So it will tell you that the quality of signal you are getting when you are exciting the PCB with some kind of voltage. Similarly, power integrity analysis. You apply some power. Obviously, the maximum power transfer theorem will tell you that you are not going to get the complete power output, right? You will get a maximum 50% of the power output you can expect if you have an impedance matching. But however, that is also not possible because of the lot of power drop will be there. And where the power drop is happening. So we have to study that thing. That kind of thing is there in the power integrity analysis. Similarly, several applications. Basically, you are after the designing of the PCB, you want to check the PCB for the different kind of electromagnetic problems and verify it, modify it. Then only you can go for the next level analysis. That is the electromagnetic interference compatibility analysis. Not only just the PCB is also part of the cable analysis as well. What are the things you study? The radiated emission or conducted emission, radiated susceptibility, conductor susceptibility. How much is the radiation your PCB is actually creating, or how much is the radiation that PCB can withstand? So these are very basic and very important applications related to the electronics industries. And trust me, 65 to 70% of the job that we have in India or across the globe for any RF engineer is related to electromagnetic interference and compatibility. On the other hand, I can tell you that EDA is one part under the MAMC. Even the basic antenna is also coming under MAMC. It's everywhere. Basically, what we try to do is we are designing a product and that is compliant to the different kind of standards. So that is very much important, EMAMC. But unfortunately, these things we are not in our curriculum. Except in Goa Engineering College, they have an EMAMC lab. The teachers are doing the experiments, basic experiments only, not that much extensive experiments. But at least in a campus like Government Engineering College Goa, they have this as a syllabus. And in IITs, it will definitely be there. And IISc, especially if you go to IISc, they have professors who are actually working in the EMAMC part, and there are some students that are doing the PhD. And unfortunately, not anywhere. I didn't see much of the areas there. The people are actually teaching or people are actually studying the electromagnetic interference and compatibility problems associated with the different kind of microwave products. And that are the actual job provider in the industry. Now, if you go something little backwards, go to our physics classrooms, or if you go to the basic initial level of engineering studies, we all study about the particle dynamics, especially the manotrons, klystrons, or gun diodes. Even I think that most of the colleges who have a master's, they also will provide you the lab for this kind of information. Some colleges will provide you the lab in the graduate level where you are going to do these experiments of klystron amplifier or TWT amplifier. And what are these things? These are the basic building block of all the high power applications. And even Manatron is the building block of micro oven. It's a consumer product. And not only that, you may need to go for the multi-packing analysis or the effects related to the secondary electrons emissions when your actual micro product is exposed with a high level radiation when it is launched to the space. So multi-packing is one of the other problems. And also you have the beam sputtering application. So there are various standard applications that is actually doing in the space related domains and also in the consumer segment as well. So particle dynamics is very, very important topic, but that is there in academics. We are studying it, we do the experiments, but we can do the simulation as well. So that is the thing, the other part. And finally, the static low frequency applications. That is from the very basic, all the days from the 10th or 8th standard onwards, we are all studying about the different kind of low frequency things, right? When you go into higher level, you are even studying about the motors and stepper motors, servo motors, all the kind of applications. Now you think the possibility of design the same thing in our software, that is also possible, including the electromechanical product or high voltage AP current applications. So let's an example of very high power cables that we use in the power supplies. Or if you are designing about the different kind of shielding for the cables or the kind of applications, or you just consider about the designing of power electronics equipments or proximity sensors kind of thing. So that is also nowadays possible with the simulation. So this is what you are seeing in here. So all these kind of applications, starting from the basic micro applications to the static and low frequency applications, everything is coming under one single license. So that is a choice you are getting there. So when you have a license of CST, this is what you can do. You can teach the students out of box. So why I say that about out of box, I will suggest you that you want to get your kids to get the job in the current market trends. So you will be able to teach them about, yes, these are the things actually needed in industries. I'm not seeing that. Microwave engineering, you study papers related to antennas, transmission lines, radar. That is not usable. No, they are all usable. But unfortunately, as a growing market, India don't have much companies. They are working on the antennas or antenna placements related to things. However, we have so many companies, they are working in the electrical components. And on the other hand, you can see that the people are interested in the electric vehicle industry. So all the people are working in the electric vehicle. So many startups are there. So what they requirement, they want to, they are not going to place the antennas over there, right? They need antenna, but they will be purchased from some companies. But what basically they need, they will be designing the PCB, but they want to make it complaint. When you want to make it complaint, you want to do this kind of analysis. So these are the 5 important topics that will be there. This is the complete overview of what you are seeing in the CST. As a CST as a tool, it is coming to, I'm not talking about the end-to-end solution, but these 5 are the most important pillars of any academic institution or research institution to make the students capable of getting a job in the current industrial. Now, that is one part. That's about the overview, capability, and job opportunities, etc. But what is there in the basically, what you want to study actually? The thing is, the computational electromagnetics. The CST is a tool which is coming under the category of computational electromagnetics. So what is computational electromagnetics? I understand because I only did the presentation in this same college. If I remember in 2017, 2018, at that time I was explaining all about the computational domains. And before that, I know that you all have studied computational domains. That's the reason if this student which is sitting in before me, definitely I will go into the detailed classes of this computational domains. But yeah, so you are professors, you already know about what is computational domains. So I'm not going in detail about the computational domains, but basically they are the numerical version of this equation. Earlier days, people are using that for basic applications. Now it is expanded to all the other applications, right? But what is the problem there? What we need to know? More than the theoretical part of Maxwell's equation, what we need to know for using this kind of tools. I'm not talking about the CST in general. I'm talking about all the kind of computational tools. How you have to use it. That is what we need to see. For that thing, you want to understand that what are the things we can do? What are the things we can use it? So you have seen that several kind of applications. Antennas will be there. Antenna arrays will be there. And that are the only things? No. You have to place the antenna somewhere and they're using it, right? You have a shape, you have a vehicle, you have a different kind of objects will be there. And you also have not only the antenna, you have other kind of things like a circulator or like a amplifiers, you are like filters. And also you can see that the other applications like PCB, several things are there. So that is really in electromagnetics. So electromagnetics is not only limited to an antenna, it's related to a lot of things. And all these things are there in industries, but the way we have to use the tools to simulate that thing is quite different. So what are the way we can address this kind of problems? Let's see. One thing is you have to first categorize this problem. I am categorizing this problem into bandwidth, or in terms of small features, or in terms of resonance, or in terms of electrical size. These are the 4 most important categories where you can categorize the problems here. So if you are considering out the bandwidth alone, you have a problem where you have wide bandwidth or narrow bandwidth. If you consider about the electrical size, you have a electrically small structure or electrically big structure. What is the electrical size? You already know. We are measuring any kind of object in terms of wavelength is called the electrical size. Then there are other objects where have very small features, tiny small features, or it may contain more number of small features. I mean, its complexity is increasing. And in some other structures, it will be having very high resonance, and some structures have very low resonance. And Maxwell's equations, even in the form of algorithms, not one algorithm cannot address all these kind of problems. That's why scientists have devised different kind of algorithms. And each algorithm have a capability to address specific problems. And that is what we are mentioning here. One thing is the transition solver, which is having 2 different kind of solutions. One is called FIT, the finite integration technique, or the other one is transmission line matrix method, TLM. So if you are using the transient solvers, they are the time domain solvers, or we can say it is a time domain version of the Maxwell situation. There's a time variant. And you may know about the FTTD. That is also one of the time domain solver. FTTD is derived from the FIT. You can say that like that. And it is a patented solver for CST, where you can use this kind of time domain solver, like you can see here. If the problem is having wide bandwidth or it is having the electrically large size, you can use the time domain solver. And what about if it is having highly resonance? Then better than time domain solver, you can use the frequency domain solver. Anything related to the finite element method. That is the prefactor or the most important or conventionally used the solver algorithm to address any kind of problems which is having high resonance. But if it is electrically large, very large structures, the preferred solver is integral equation. The reason why integral equation is preferred here, because it is using the surface discretization method, or it is only calculating the current and charges from the surface. If you're using any frequency domain technique like FIT method, that is time domain version, but we can say it is a volumetric method. And frequency domain solver, that is also the volumetric method. If you want to solve the kind of problems using the volumetric method, you have to discretize the surrounding media as well. So it will increase a lot of pain for the simulation. It will take a lot of time for the simulation. So that's the reason these surface integral or boundary integral methods are generally preferred for the electrically large stretches. But that cannot be used for so much electrically large stretches. That's the reason the ray tracing methods are more preferred. We call it as asymptotic. The reason is they are not that much accurate like these full wave methods. Oh, this is called a full wave method. They are using the brute force technique, right? They are directly implementing the Maxwell's equation, even though if I say brute force method, it is an exaggeration, like you know. There is still approximations will be there. Any numerical computation is full with having the approximation methods. But still, it will be having less approximation when compared to the asymptotic method, where you are using the ray tracing method. Basically, the shooting and Bunsen method, that is the preferred choice of this kind of application, very electrically large structures. And here comes the low frequency problems. When it is having a high frequency problem, there are low frequency problems. Unfortunately, Maxwell's equation need an additional stability factor when you want to go for the low frequency. So that's the reason there are specialist solvers are made for that application, especially the electrostatic or magnetostatic problems, or static current, or stationary current, or low frequency version of the frequency domain and time domain solvers that are generally used for the low frequency applications. And if you go in more detail about the MEMC or ED application, the preferred choice will be the dedicated solver for the cables as well as the PCB. Basically, the partial element equivalent method or partial element equivalent circuit model, or the TLM method, transmission line matrix method. They are preferred when it is come to the PCBs or the kind of. And not only that, CST have around 17 plus solvers are there. So these are one more the solvers. There are solver for the multi-layer structure, that's called multi-layer solver. There is specific solver for the eigenmode calculation, that is called eigensolver. Then there is a solver for the temperature and structural mechanics calculation, that is called thermal solvers, like conjugate heat transfer solver or transient thermal or stationary thermal solvers. Then structure solver is there. Then you have solvers for the particle dynamics. Oh, these all algorithms will not be suitable for the particle dynamics. Okay, so there you have to, because this using the electron propagation, photonics and application. So there will be very difficult to use. It is very difficult for using these algorithms for the application. So they have a particle dynamics solvers are there, very dedicated solvers, Wakefield solvers, particle tracking solvers, particle in-cell solvers. So it is a collection of around 17 plus different solvers and the hybridization between these solvers. Anyway, we will discuss about these things in a more detailed classrooms later, and depending on your interest. So this is basically what is the basic content of any CST session, where I have to introduce you the different methods that you can use for the application. Now, just to go into some of the applications of what we can do with the CST. I know I'm talking about only 1.1% of the 100% applications that is out there. So these applications are, one thing is the antenna design. So when you go to the antenna design, there are several ways you can use the antenna in CST. One thing is, as I mentioned, you can take the antenna from Antenna Magus. So Antenna Magus, I don't recommend for everyone, because if you are really enthusiastic or if you want to do the complete research, you want to make something new kind of antenna, Antenna Magus will make you lazy, because Antenna Magus have more than 400 plus different kind of antennas. So you're very lazy, but it is useful for the students, or you are using for the industries where they don't want to spend hours of time for designing an antenna. They can just pick the antenna from Antenna Magus, synthesize it, and take it to the CST, and then you can use it. But for a researcher, it will make you, and if you are working on design on antenna, then Antenna Magus will make you lazy. That's it. And on the other hand, there are different kind of product as well. It will support, because CST as a tool, it will support all the global card format from any kind of software. For example, if I say about CATIA or SolidWorks software, where the people are designing the antennas, you can take that antenna directly to CST and do the performance analysis. Or you design the antenna in CST itself. It's how the complete card package. You can design any kind of geometry. Once you design the antenna, I always prefer, if you are designing for an industrial application, I prefer you design along with the platform where you're going to mount it. For example, you are designing an automobile antenna. I will prefer you design the antenna first, then you import an automotive card geometry and place the antenna over there, and then you do the analysis. Then you can see the perturbations. Thus, some perturbations are not allowed. It will create a lot of noises, or it will create some problems, some gain distortion towards some particular angle that is not be applicable all the time. And it's always preferred to understand the cosine interferences if you're placing an antenna over a geometry. So it is always preferred, if you are designing something for the industry, basically you import a geometry, you place the antenna over there, and then you do the simulation. But as I mentioned before, now we are not talking about the passive antenna structure alone. We have to discuss something more about the active antenna structures, where the antenna, the structure is equipped with the additional circuitry, right? You have amplifiers will be there, you have a phase shifter will be there, you have power divider will be there. So everything you have to do the design and add it to the antenna, then only you will get the recorder output. Or if you just design the antenna, then you try to make it in the market, it will not be accepted, because that antenna may have an impedance mismatch in the other associated circuitry, and nobody will use the antenna alone, right? Antenna cannot work alone, it needs an additional circuitry. So that's the reason you need to do the circuit simulation. And finally, the multiphysics. Almost 90% of the time, none of us is bothered about what will happen to the antenna when it is working continuously. Because what will happen, when you see, if you're considering with the hyper antenna, then it is continuously working, it will create the temperature out, and this temperature can create some shape deformation in the antenna, and that will result in a different pattern than the one which we are intended for. So that's the reason the thermal simulation is one of the most important, and not only thermal, thermal structural simulation is one of the most important thing in the industry as well. And academics, people are not much bothered in India, but in Western countries, not the case. People will be going for all the aspects of that particular antenna or any kind of product you are designing, but because they are not just intended for a PhD over there, they just want to get a job. Or to get a job, you want to get an attention. If you want to get an attention, your product, whatever you're going to output it, that will be worth. So that's the reason they make a more perfect thing. In India also, except in IITs, I have not seen that much trend over there, but now I can see that there are certain changes happening. People are getting more fund and people are doing the most research applications. So what I personally suggest you go for all the challenges which is over there in the antenna design X, not just designing of the passes. Now, if you go to some industrial application over there, so you can see that this is a very smart projector, and you can see the size is very small. And if you open that, geometry, you can see that there are so many different kind of structures out there. Some will be battery, some will be somewhere it will be electronics equipment, it having an aluminum frame, and you want to place your antennas. So it is difficult. So here comes the antenna makers, the one which make you be lazy. The antenna makers have a lot of different kind of antennas, and what is the thing you want? You see that you want to place the antenna somewhere here, and it's very small place. So you want to design an antenna which is relatively small and should have the omnidirectional pattern. So you have to search for the antenna over there, or you design yourself in the CST. It will take some time, but you can do it. And if you select a particular antenna over there and you can place it over here, and what you will get your resultant pattern. You will get the near field pattern, that is also important. You get the far field pattern, the pattern you can combine together, and you can also see the coverage efficiency of the particular antenna. So after doing all the studies, then you go for your certification, especially when you are designing something for a product. The product has to get certified from the relevant agencies, then only you can go for the mass production. So that is one of the important things. But as I mentioned, antenna cannot fit anywhere alone. You need sometimes you will experience some matching problems. As you see that if you don't have the proper impedance matching between the antenna terminal and the coaxial cable where you are going to feed the power, what will happen? It will create the high level standing wave ratio. The standing wave ratio will be high, or you say that it will create the standing waves. The reflector signal will be high. It will create the ratio high. So generally, our interest will be below the 2.5 SWR. It will go above 5, and we cannot accept it. So you may need to add some proper impedance matching network. That is one of the things. Second thing is, as we are all interested in the reconfigure antenna, whether you are going for the pattern diversity, frequency diversity, or polarization diversity, you may need to add certain essential components, including the pin diode or connectors kind of components to make it tune. So that is one of the other applications. The final one is the feed network. For area antenna, you are not going to feed. If you have 100 elements, you are not going to use 100 coaxial cable over it. You are adding a feed network where you can apply only one single excitation. And not only the feed, and you need to add a phase shifter. Sometimes you need to add a phase shifter, obviously. So all this feed network, one of the important things. Just like you can see an example here, you have a dual patch antenna, and if you add a dual patch antenna with excited here at the same volt and here at the same phase, you will not get the exact or combined pattern. You will get a pattern like this. This is not that much good, right? You will get two patterns just add together. No, that is not sufficient. Second thing is you need to get in an intended frequency of operation. So what you can do is, one thing is you have to correct the impedance matching using an impedance matching macro. There is a macro available in CST. You just use the macro. It will create the circuit like this, and you will add to your antenna. You will get that impedance matching network and the specified frequency. And that is not the case. Now you needed to go for the amplifier as well, because you only establish the matching performance. Now you need to add a small amplifier for that thing. That amplifier will give you the necessary output, right? So the amplifier design, that is the other part. And not only the amplifier, as I mentioned that you need to add a phase shifter, because if you add, if you feed one terminal with a 0, and the other terminal with a 0, then you will not get the actual radiation pattern. What you are getting is just the addition of two different patterns. So if you want to get a single performance like with a high gain, what you have to do is you have to feed one with a 0 and one with the 180 degree output. So for that thing, either you can use some changes in the feed terminal, or what you can do is you can add a phase shifter. And the phase shifter is one of the integral part of most of the 5G antenna base. So all these things you are doing in a one single shot. The other things which here coming in the mind is a millimeter wave antenna design, that is especially for the sub-6 gigahertz, not for sub-6 gigahertz 5G. It is actually for the 28 gigahertz or 28 to 39 gigahertz of the millimeter wave band, which is one of the area of interest for the companies when it comes to the 5G spectrum. So here what you are seeing is a multi-layer antenna structure, and this is an active antenna. About this one, this is the passive antenna, and this is the active elements here. Over here, below that there will be a feed network, like you see that equipped with a phase shifter to form the beamforming. So why this as I mentioned before, because you all are the professors, so you know well what are the things associated with 5G, and 5G the most important thing is that it is having very high bandwidth. Not only that, it is in the spatial division multiplexes method, where you are going with a different kind of beam scanning. That is one of the essential part of any kind of 5G antenna structure, whether it is a baseband or it is associated with your mobile, basically the mobile phone antenna or any IoT device sensor equipped with a 5G structure. Now, one thing is the complexity and the designing of the structure, and second thing is how efficiently you can place it over the particular target. So in this example, it is a target is a mobile phone, and now you see that you can see the two different kind of pattern over here. This one is looking very nice, no perturbation, very smooth curve, and here it is full of perturbation. That means there is a distortion in the gain as well. Why it is having this one? Is because of the material which is used for the cover, right? Like you can see that when the antenna is radiating, the radiation, if it is properly radiating or if it is getting reflected multiple times, and most of the times, remember, if you are using a metallic case, if you have the high level of radiation reflection, you will not get anything out. If you're using a dielectric based structure, for example, glass panel structures, what will happen? Because of the dielectric property of the structure, it will not be going to provide you the complete smooth transmission of the electromagnetic wave from in and out. So that will result in this kind of wave. So other thing what we can do is, as I mentioned, use an FSS structure. What is the significance of FSS structure? Just like antenna, you can also represent an FSS into a series of RLC chain, right? It contains LC components. Specifically, it is an LC network. Basically, you can say it is a filter, mostly the band pass filter. It will only allow a range of band of frequencies in and out. So FSS are metallic structures embedded over the dielectric. There are different kind of FSS structures are there. You can use a tripole, or you can use a jersey link cross. Ring structures where the circumference of the ring is equal to the electrical wavelength, the band of wavelength of the frequency. There are several standards will be there. But end of the day, you will have an FSS structure like this. You can see that, and it will have a passband stop band performance you can address. And if you use that kind of structures, as I mentioned, it will not prevent any kind of radiation in an indented band, but it will block all the radiation in the other bands. But if you're using a lens structure where lens is a dielectric material, if you use it because of the dielectric property, it will not be a smooth performance. So you'll get a more radiation. And even though it is ideal, looking like ideal, you'll get a much better response. So that's one of the other things. One other significant thing when you're designing any kind of 5G structures, not really just a mobile phone, I'm telling you that you use the platform also. The other thing is the 5G. For the 5G, you may need to calculate additional things like the cumulative distribution function and effective isotropic radiative power or SPD. All these kind of standard factors will be there which you have to calculate it, because then only you can say that whether your antenna is compliant to the 5G standards, or you just simply say that the 3GPP. What is 3GPP? Third generation partner project. They are actually doing the certifications, different kind of standards for the 5G applications, right? So according to them, you need to have an ALP of 10.5 dBm with the cumulative distribution function is around 50%. So if you want to get to the 50%, you want to do the simulation, right? That is what you are seeing here is the envelope pattern. Okay? So from the envelope pattern, you need to get the cumulative distribution function ERP, and that should be satisfied. Then only you can say that this one is working as a 5G antenna. So not just designing in the antenna may not make it as 5G. Okay. Now other things are there. I am not going to talk much about these things because it is not part of the interest of the session. But however, it is the most important thing. The EMEMC compliance. So like what I was saying about if you're considering about the PCB of the mobile phone, you need to go for signal integrity or power integrity analysis. Then you want to see that how much of the temperature rise is there, because as the temperature increases, most of the ICs, transistors, whatever there it is in the PCB, that may go into damage. So you want to first address as well. Then second thing is the antenna to antenna coupling, antenna to PCB coupling. There are so many things are there. Actually, I removed all the slides to save the time. Now the antenna array. So here, whatever the study we are doing with they are all including with one of the 60 element antenna array, which is operating around the 5G frequency only. And what we are going to do is we are to just discuss about what are the 4 different methods when you for the antenna array analysis. One thing is the unit cell approach. Second one is the full antenna array with the sequential excitation. Sequential excitation is one of the favorable type of excitation doing in industries, where you are exciting the every port one at a time. And simultaneous excitation is where you are applying excitation to all the port at the same time. And we also do develop one method for any kind of structure which is running on frequency domain method, that is called a DDM, domain decomposition. That is also I will show you that how the performance will be varying. So for this one, what is the basic workflow? Just you design the antenna, or you just pick up an antenna from the antenna makers. So we have selected one antenna from the antenna makers. Now what you do is you go for the unit cell analysis. What is the advantage of you in using the unit cell analysis? You will get 2 important parameters. One is active element impedance, second one is active element pattern. What is active element pattern? When you do the antenna array analysis, just for antenna array analysis, you will see that you have a different S11 parameters, right? If you have an S11 for one element, it will not be completely true when it is come to an antenna array. So every element which you have a different kind of S11. What is the reason which is having different S11? Because of the coupling and the elements. So that you can actually understand when you do the unit cell approach. Second one is active element pattern. So the pattern which you are going to get, which you're actually going to represent when you go to create the full antenna array. So industries, they follow this unit cell approach for the optimization of structures before you are going to create your actual antenna array. Because if you're creating in a big antenna array and it will take a lot of time, then after that only you find out that, oh, this is need to be optimized. Again, you run the simulation, again you see the work. So it will take a lot of time. That's one of the best approaches. First you finish your work with the unit cell, optimize it into the intended radiation pattern, then you go for the full wave method. So in the full wave method, what you have here is you can create your own antenna array using the antenna array task. So you can create the antenna array like this. You have the layout, and there are 2 different ways you can excite. One method I told you that you can excite all the elements at the same time, either using the simultaneous excitation where all the elements will be excited at the same time, or sequential excitation where you have each antenna will have a separate radiation pattern that you can combine to see. So what is the advantage of sequential excitation? It will, when you go for the post processing, you can get the different scan patterns. It will save a lot of computation time, but however, it will take some time for simulation and the pursuit as well. Second method is how you can accelerate the speed in sequential excitation method by simulation by zones, where you can categorize the elements into separate groups. Because you cannot, this is not a perfect grouping, but still you can see that all these green elements may have the similar kind of radiation coupling, and all the other elements will have a different kind of coupling, but that is not completely true. That's the reason this is the most simplest method, but I will show you that what we can do in a real antenna array case. So that's the thing, when you do the sequential method, you will get the pattern for each element separately. Or then you can later you can combine it, you get the intended radiation pattern. Okay, so that is what you are seeing. Even if you like a simulation by zones approach, you change some of the elements into groups like this. You have this are different groups. If you change in different group, also you will get the radiation pattern. Like you can see that which is a perfect grouping method. Here you can see that if you consider about these blocks, right? These blocks, all the elements have a same amount of neighbors. That's why these blocks are categorized into 1, 2, 3, 4 different groups. Similarly, you can see that these all have a different coupling mechanism. More interestingly, you can see in this one, this is having less number of groups. So you can see that all these elements have the same number of neighbors, and all these have the same number of neighbors. So depending on the number of neighbors are there, you can categorize into the elements into groups. So you will get to some result, and which will be close to the one which you get in if you exit all the elements, because you are actually classifying the elements in terms of the coupling. So that's the second thing. You can do the scanning, because 5G, if you're talking about 5G or IoT, any kind of application, 4G also, beam scanning is one of the important things. Like how you are able to do the beam scanning, a lot of things to study. The other thing is domain decomposition method, which is like divide and convert. We are selecting certain number of elements, and we don't need to do the simulation of all the elements, because each element will be representing a particular group of elements. So similar thing what we have seen in the simulation response approach. Something here, but in this case we are using only for the frequency domain applications. The reason we are using this method, because I told you antenna array is best simulated using the time domain solver, but unfortunately certain high resonating structures will not give you the best result or in time, best time in time domain solvers, because certain methods, certain antennas will be best suited for the frequency domain because of their high resonating nature. So we have to use frequency domain solver, even though it will take a lot of time on memory. But using the DDM approach, that is a recent addition to the different kind of antenna array method. Like you can see here, before the implementation of the DDM, it was taking around 180 GB for the same antenna array. Now it is reduced to 34 GB. So that is the kind of reduction you will get, around 64% of reduction you are getting for the memory, and 6 times speed up for your simulation. So that is one of the basic addition or basic method you can follow when you're doing the antenna array analysis. Somebody is interested. But the result, if you on the other hand, the result, they don't have much variation. I'm not saying that 100% matching, but they will not be having, but not have much variation. Now, just designing of the antenna array is not sufficient. You have to place the antenna array in some towers or some kind of structures, right? And here comes the hybridization requirements. If you are considering about this mast, and if you do the full simulation using the time domain solver, not only the mast, the surrounding media also has to be discretized, which is a lot of time in time domain solver. So best thing is you can do the hybridization where your antenna is actually operating in time domain solver, and you for the mast structure you can use the iterative solver like integral equation solver or MLF. So it will give you the same kind of response, but in a very fast time. Other thing is you can do the propagation model analysis, especially the 5G coverage analysis. Just like you can see here, you can have this kind of building. You can place your antenna in one point. You can place the antenna. You can try to move that antenna. You can see that what are the kind of interferences actually happening to the receiver. So basically, you know that in these studies, right? These studies are nothing but a propagation analysis, where you are actually understanding the multipath reflections. Again, multipath reflection in terms of noise and loss condition, like the rise fading, Rayleigh fading. Nowadays, you know that these things are in the curriculum mostly for like this. So you are better understanding that how this wave is actually going to propagate. So you can do the ray tracing method to understand the propagation, right? So this is one of the most important thing, and especially relevant for if you are working on the 5G application or if you are working on IoT kind of application. Now, most important, you do everything, but your human safety is more important. If you are not complying with the international standards for the base station, I am repeating, ARPA-Mensa or ICNRP standards. Or if you're considering about the handheld device, the SAR is one of the essentials. And again, it is not completely true for the applications, including millimeter wave application. There, the power flow is more important than the SAR analysis because of the penetration level of the radiation into the body at a millimeter wave is phenomenally less compared to the subsystem frequency bands. And what are the things you can do with, but when you are doing this S-first analysis, one of the most important thing is the accurate phantom model. So we have a phantom model which is provided by input in the latest 2021 version. Before that, you can directly download us from our customer database. So it contains different kind of Voxen model, the model which including all the kind of new materials, each material having the different dielectric property. The dielectric property that can be tuned to the relevant frequency. Because if you are not able to tune it, then you will get the different result. Because every part of human body is a frequency dependent. So you are getting a 2 gigahertz one result, you will get a 5 gigahertz another result. So it is always better to tune it for the intended frequency. So that capability is already there inbuilt with the model. And you can place your antenna or mobile phone along with the antenna. You can see the SAR analysis as per the standards according to the FCC. And also you can even understand the temperature distribution because of the antenna which is placed near to the phantom. So these are one of the most important studies that will be conducted for every mobile manufacturer, any handheld manufacturer. Next one is an example of a wearable antenna. Again, it is operating at around the 3 to 6 gigahertz of frequency. It is a slot antenna like this, you can see here. So it is operating at this particular angle, and this is already a paperwork published in some years 2012. And we are going to place this antenna over a human phantom and in the position like this. So you have the radiation pattern. I just want to tell you that this is a radiation pattern without placing over the structure. When you place that antenna over structure, you can see there is a perturbation you can see here. So obviously that will happen when you are when your antenna is actually going to operate along with the platform. Okay, because of the platform it will have changes in the pattern. And you can see the radiation pattern over here. I didn't, this is with the three different methods, but I only include one method information to save the space. And also you can see the fidelity of the particular structure as well. So there are so many things that will be there. Fidelity means you will get the same response, accurate response at all the different locations when you are the different viewing. Now before completing, I want to just to show you some more things. One thing is because as I mentioned that antenna is not along the champion here, you may need filters will be there, isolator will be there, circulator there, so many things will be there, right? What we have in CST is we have a FP3D, that is a frequency filter design, a 3D tool, which you can use for the synthesis of any kind of cavity filters. And then you can use the filter tuning that can be done in CST, and you can do the complete assembly, and you can do the multiphysics analysis as well, because these are high power application structures. So there are 3 ways you can design the design a filter. One thing is using FP3D, or you can use the FS3D, or you can manually design the filter structure using CST, or you can import from an external card. So what are the things you can do? I just summarize like a synthesis, tuning, assembly, and multiphysics. So these are the things which I just giving an overview of what are the things are available there with the CST. So what you have seen is we have different kind of solvers are there, and selection of the solver is very much important. You can do the multiphysics analysis of the particular structure. You also have a design studio which is equipped with different kind of components, and a hybrid solver to get the acceleration, and different kind of methods you have seen using for the antenna array. What are the methods? One thing is using the unit-cell approach, or use a sequential simultaneous design approach, or using the DDM method. Then there are different kind of applications as well, but I removed all these applications because I think that it's preferred, your preferred choice would be on the academic and the education section. Basically, there's antenna applications. So if you have any question, you can ask me now. Then after that, I will open some of the models and I will show you that what are the capabilities of CST based on.
Yeah, Sumit, I have a silly question. Can I ask one silly question?
Okay,
Yes, sir,
sir.
please.
You can ask.
Yeah. Actually, we are using right now for the 4G bandwidth only. Okay. Right now we are handling with the Bluetooth headsets right now. Any radiation it will be surrounded on there for headset or Bluetooth earphones or Bluetooth or any Apple plugins. It will be any happen thing on that radiation.
Okay. See, if you have a Bluetooth headset, basically the Bluetooth headset is powered by the same signal, right? Because it's a
Yes.
wired connection. So whatever the signal is coming, it is, I will say it is the more power than if you're using the wired channel. Because in wired cable, you don't need to, you have your speaker, whatever the coil is there, it is actually vibrating. It's based on the input, say, electrical signal is coming here. That have two purposes. One thing is it's how to reproduce that sound there, and also it is to the power that particular module. So there are two purposes there. So more radiation will be there. So if you are, but again, wireless Bluetooth test sets are not completely ruled out from any kind of health issues. But if you see that, if you are using a mobile phone, if you talk to someone in 45 minutes or less, somewhere around 45 minutes, you can see that you are getting some pain in the ear, or you can see some heat experiences there. Why? It is because of the any kind of RF radiation have thermal effect. And you want to see that really, what you can do is you can do the simulation of the same thing and for the thermal analysis, not just for the SIR. Instead of that, if you go for the thermal analysis, then you can see that the amount of temperature actually going to produce that by that particular mobile device. And it is not going to happen if you use it for 5 minutes or 10 minutes, okay, you will not get feel that much. But if you speak continuously for some time, then you can see that the effect is coming. It is a mobile phone. It's the same thing, but when compared to the mobile phone, Bluetooth headset is taking the very less power. So you don't feel that much temperature effect or thermal effect is there. And to till this stage, nobody proved that this kind of headset will create any kind of harm to our head or anywhere. But doctors are suggesting as long, because these things are introduced around the 15 to 20 years only. And we cannot say that whether it will have a large impact, because these are not continuously using. It's not like you have a macro oven, and when the oven is operating, you put the hand inside it. So you will see that effect immediately. These kind of things will not see that, because that is high power thing.
Also, sir, to add upon to it, like it also depends on the maker, like which brand you're using, because certain companies give a very due diligence to these radiations, and they take human comfort parameters and the health into the consideration. So that's where they implement certain tools to find out the radiation levels. So before coming up with the final design, so they test it, validate it, then they go for manufacturing. So it again depends on the makers, like which brand you're using.
Yes, Srinivas. But I have another doubt also. Right now we are in 5G in sub-6. We are using, right?
Yes.
Yes.
3.5
Yes, sub-6. But some of few companies, some Xiaomi, Realme, some of devices they are already introduced 5G technology. They are using a little bit N1 or N2 like that only. Which type of one, if you have figured it on fixed mobile one, and which one is it will be better than for sub microwaves on sub-6 one? Actually, in Apple, they are also introduced in 5G, and Samsung introduced 5G, but they are using only 2 to 3 types of bandwidths only, right? N1, N2, or N5, N7, like this only. Okay, right now the bandwidth of N257 or any of like that, which bandwidth of 5G mobile and 5G device it will be better than in right now?
See, it is not about the betterness, it is about the standards every country is following, because every country is following separate bandwidths. I can show you that.
Right.
Even
Yes.
some couple of years back in 2018, I had a discussion with one of the Indian's telecom additional director. I visited him in his office. So that time, government of India was planning on the E and V bands. You can say that E and V bands is on 76 gigahertz and 86 gigahertz.
Okay.
And I have seen that some people are even working under 300 gigahertz. And one of my customer is working under 486 gigahertz. If you understand that, different people have a different. See, if you increase the frequency, what you are getting is you are getting high bandwidth, right? You get 1,
Yes.
2, 3, 5 gigahertz bandwidth, because as the frequency is increasing, your one thing is you are getting the bandwidth. If you are getting bandwidth, that means you can transfer more data. But
Okay.
what is the practical problem? Practical problem is if you are increasing the bandwidth, your wavelength will be more and more shorter. Your range is limited.
Yes.
That is the most important problem. Your range is limited. As to this point of time, I have seen that most of the array base station manufacturers are worrying that they are getting maximum of 100, 200 meter range. So every 100, 200 meters, you want to place a base station. That is highly expensive problem. So if you increase in the frequency, this is one of the problem. I'm not saying that it is not a thing, but if you want to know more about the effect on human body, just look at this one. So there are different kind of radiations. One thing is we call it as ionization radiation, other one is non-ionization. Ionization radiation is the most important thing, like UV, X-ray, gamma. This going to damage our tissues, etc. Non-ionization radiation, which is having the low power. So you can say some static fields like MRA. MRA again, you can see that if you continuously expose to MRA for many times, then it will damage. Or you have using the other low frequency things. One is sub-6 gigahertz, the same thing you are saying, which actually going to penetrate into harm to the body. That is the current SAR analysis. That is the significance of SAR analysis that we do. Because all the GSM communication from 800 megahertz, whatever we are using up to 2.8 gigahertz, which 2.6, 1.8 gigahertz, 2.6 gigahertz, which we are using for the LTE, and even WiMAX 3.2. All these things are penetrable. And if you go to the sub-6 gigahertz, majorly the 3.5, 3.8 band of 5G, again it is penetrable. But if you go more than on the millimeter, what will happen is it is not exactly penetrating into the human body, it will actually go damage on the skin. Not the damaging, the effect will be lying on the skin instead of it is penetrating inside. Okay, so that's the reason there are several international councils. I told you about ARPANET and ICNRP. That is one thing. Then second one is IEC, IEEE, and other local governments is in every country. Their own state protection methods will be there. They will be having the local standards. So then again, there are two ways the people go for: occupational and generative public scenario. Mobile phone kind of thing is occupational, basic occupational. But in other things like base station, you know that thing, around 10 meter radius, you should not go in close to the tower, right? They will already say that they will put some notice board with a skeleton and head, danger. Because that area will have the maximum power will be confined, that's the reason. And you know about basically the SAR analysis, whatever we do with the SAR analysis and all these things. But what does the area of interest is this slide. You can see that India is now currently operating 3.3, 3.4. Even in Samir, Chennai, they are also operating in the same band of frequency. They are preparing the 5G test bed. And this is one of the area. But in USA, Japan, they are operating at a millimeter wave. They are also operating, they are doing the research and everything. So this is in millimeter wave things. And USA is also doing something on the 3740. We have a plan in India for 76, 86 gigahertz also. Some people are working under 480, as I mentioned before. So what actually happening is, you see the bandwidth. The bandwidth is very high, right? So if the bandwidth is very high, that means you are actually able to transfer more bits of data. And all these methods, they are using the QP, SK, or a method. One is if you're going with a higher one, it will be like a QAM, 150 megahertz or plus QAM. That is a different kind of switching methods they are using. UPSK or QAM method will be mostly employed for all the 5G. But 5G, there are several things in there. One thing is the penetrability. One thing I hope that you already know what applications are there. So the penetrability, including the how the gradient, the slow wave gradient, Rayleigh fading, and all these things will become in the future when it is actually propagating out there. That's the reason RF planning is one of the important things. And it's also depending on the frequency. Because if you go, that's why I'm saying that. In fact, I'm telling you not only about the just to get in the mobile to mobile. Okay, if you have a building construction, just a concrete wall or a glass, it's have a different frequency response, right? It's path loss. Whatever the path loss is going to create at 3.5 gigahertz, it will be one different. Maybe it will give you only 17 dB, but at 26 gigahertz, it will give you 24 dB path loss. So again, that is most important. That's the reason I will tell you that if you increase the frequency, one thing is how it is affecting the human body. Second most important thing is not affecting the human body, the area it can cover. It cannot cover much area. It will be limited. So it is expensive. But what is the advantage is here is the geometry will be very much compact. And one of the other problem is that for the uplink and downlink, there is some restriction on the power gradient as well. Because total ARP is somewhere it is restricted to 40 to 53 dBm, right? So 40 dBm is just 10 watts to 120 watts. Some testers are done at 3100 watts also. But again, on the simulation profile, you cannot put a 3.1 kilohertz of watts in power for the 5G in a public place, right?
Yes.
And one other thing is that currently the research which is going up to 12 kilowatts. So why it is need a high power? Because you need to get more coverage. But the problem is that there are two more challenges are there. Again, if I go in more deep in the thermal problem, the thermal radiation. If you increase the power of the antenna, what will happen? It will create more temperature. If you create more temperature, there is a chance that it will create a dielectric breakdown also. Because every antenna is equipped with a dielectric slab, right? That dielectric slab may not withstand that kind of temperature rise. If you, for example, if the temperature is above 200 or 300 degrees Celsius, it will can damage. And second thing is the same temperature rise can accelerate the electrons. Unfortunately, it will not be like the effect in the space. Where space, the secondary electron emission will be there. In normal and under normal circumstances, secondary electron emission is not possible, but it can give more kinetic energy to the electrons. So it will have a more radiation performance, some different radiation performance than the one which is intended. So temperature you have to limit this. So that's the reason all these kind of antenna will be equipped with the heat sink and heavy fans. And fans is not that much possible like what you can do the ideal case. I will show you an example of an antenna with body. I just 1 watts of power supply. So this is what you are seeing in 6 gigahertz. You have penetration in the body, and in millimeter wave you don't have any penetration, but the effect will be only on the surface of the human body. And you can just ignore this one. And so this is a thing, two different band of frequency. I'm just skipping this one. These are not important thing. So basically, after sub-6 gigahertz, we will be focusing on the specific absorption rate, because it is actually actually mentioned that how much is the power penetrating into the body. But in millimeter wave, we don't need to worry about how much it is penetrating, because the effect mostly will be on the surface of the body. So that is the basic difference between the sub-6 gigahertz and millimeter wave in reality along the human exposure analysis. But only about the power gradient and everything, I will tell you that you need a high power because it's having very low coverage. But higher bandwidth, you can give more data. You can go up to 10 gigabytes per second, right? That kind of speed.
Okay.
I hope it is clear for you.
Yeah.
Okay,
some mobile companies are they're creating antennas with the complete through mobile. I mean, all directions they're covering antenna. How it will be possible on that?
See, that is the beam scanning, right?
Yes.
Yeah, 5G antenna, it is employing the method called a spatial division multiplexes, where you don't need to rotate the antenna like that. That is the reason I will tell you that. In 5G, we are using only the active antennas. So in the active antenna, active antenna is equipped with a phase shifter matrix. So this phase shifter will provide you, mostly it will be like a default matrix will be provided. So by the time to time, it will give us a switching. We provide the necessary time pass. According to that, it will switch the different directions. So what it does is it will scan each angle, each direction. So whatever the intended radiation, intended area is provided, it will go scan in all. Maybe minus 60 to plus 60, minus 45 to plus 45 azimuth and elevation. So what they are looking for is the envelope pattern. Envelope pattern is all the beams which is scanning will combine together. So because it is fast switching, right? Because fast switching, you will not feel like they have separate beams. You will see like a single beam only, which is having the wide coverage. So instead of placing one omnidirectional antenna, they are using a huge antenna array. Each antenna having having a very sharp beam, but which is scanning in a fast mode in left to right, right to left, and up and down. So what you see is when you look into from one point to that, you will not see separate beams. You will see one single beam because just like our fan is rotating, right? When the fan is rotating, we cannot see like each leaf, right? We'll see it a complete circle. So because the speed of switching is in microseconds, mostly microsecond, millisecond speed. So we don't experience that because for our eyes to see something in stationary, at least we need a 60 millisecond or more, right? That's the kind of vision we don't have. We have something like a vision experience, something like that. Medical science will tell you that you want to see once object is stable, you need to get that image for at least some period of time. We need that information in our retina. But this is a very fast switching, we don't experience that thing. That's the same thing. It is coming into the data, traveling to our mobile phone also. We don't see that one, but it will be switching left and right.
SOC also, it will be the same process on doing on that.
Which one?
System on chip process also.
Yeah, anything basically what people are doing is it is when the system on chip or anything, whatever it is. Basically 5G, if you are looking only on the 5G spectrum, 5G they generally prefer only the active elements, active antennas. So each element of the active antenna, each element is connected with a separate RRE block, right? RRC block. So RRC block will be like having its own amplifier and other associated. So unlike in 4G, what we do is the amplifier separately, right? In 5G, it is only one power supply. That's power supplies go to the amplifier and amplifier to the antenna. That's the reason you need more power in 5G. Because you need to consider about the amplifier loss as well. Now I will show you some of the things in CST, very basic. So this is a CST, I had did a lot of project, but basically you can see the CST graphic user interface. If you click here, you can see that there are 5 categories are there for high frequency, cable, low frequency, particle dynamics, thermal and mechanics. So everything is single license only. Similarly, here you can see that assembly and schematic. These are actually for the circuit simulation. This is also PCB and packages. These 3 are single license. Then you have a antenna makers. I will show you antenna makers. Then you have filter designer. You have chip interface. You have a FES3D system simulator, Opera. There's so many different kind of products. Let me first show you the antenna makers. So what I hope that you are familiar with antenna makers, right? So antenna makers also have the chip antennas also there, RFID antenna structures are there, and reflectors there, different kind of antennas will be there. So this is a basic graphic user interface of the antenna makers. This is a portion version. Just later you will get the education version as well. If you are going for the research, you will get the research part, research version. The research version is something like this only. So you can categorize it, what you want, radar or smart devices, mobile communication. If you say, if you are required, you don't need actually basically, if you go for the cellular band, you want GSM, UMTS, LTE or 5G. If you select 5G, so you will get to some examples of the 5G. You want for base station or you want to go for the mobile device. If you just click, you can select that, okay, which N78, N79, N257. If you select N257, it's around 28 gigahertz, right? So it is what you're providing is, it will provide you some kind of structures that you can use to for the specific application, for the mobile antenna. It's not for the base station antenna. Okay. So similarly, you will get all the kind of antennas here, horns, wires, reflector. So you can select the frequency, you can design it, here itself, you can synthesize it. If you synthesize it, you will get the corresponding pattern as well. Okay, just like here. So this is the one which I already simulated. I don't want to simulate it again, just before showing you that. So you will get some complete structure along with the dimension as well. You will get an output. Report will be there, and also you have a library of substrate. So if you go there, you can see. Okay. Oh. Clear filter. You can see that it's having a material of all the different kind of substrate with relative permittivity, tan delta, substrate height, copper height, and everything. You can see that all the kind of materials will be there. So this is a material library. So it will be useful for you because you need to search in internet. You get the complete data from here itself. Or if you want to design for waveguides or connectors, like connectors, if you see that, click here. So you will get the different kind of connectors. FCS connector, SMB connectors, UFL connectors, SMA connectors. Okay. And also if you want to go for the radomes, like I mentioned, so this is for the blade antennas, air fragile radomes. So all these radomes are there. So everything you can take from here. And you have a toolbox, which is have a data conversion, metrics will be there. You can do some calculations, like you can see the frisk transmission equations, or system temperature you want to see, or gain of an aperture, or transmission line things. You can calculate the rectangle waveguide. So all these things will be there. Also, you can get the complete PDF of the thing you did, information, and also you can export the complete thing as a report here. Or if you want to just export the model, for example, I want this model in my system, I can export into CST. You can select a model, just export it. So you will get the complete parametric model of the antenna. So you can design the antenna array also. Your option for the antenna synthesis, array synthesis, you can synthesize any antenna. Okay. So all the information will be also provided over here. So this is antenna makers. So it is having around 400 plus antennas are there. Just like that. Okay. Arrays, transitions, constructions, variations, dielectric antennas, horns. Well, like if you say the dielectric antenna, you can see the chip antenna as well. You see the chip antenna. So nowadays everything is equipped, right? All the kind of standard antennas will be there. Now, if you come to CST, you can see you have a component library over here. You can select any component. For example, you want a 5G antenna with a phone. So you will get a 5G antenna with the phone. See? And also you can do the SAR analysis also here. So this will have a complete phone geometry along with the 4 antennas will be 3 antennas will be there. You just click here, you can open it. Okay. Similarly, if you want a filter, see all the filter like integrator filter or triplets is there or planar filter. You click here, it will be open here. So you can use it, you can do the simulation, right? So this is a basic GUI, but I'm not going to explain this one. Next one is, as I mentioned, this is one single license what you're going to get. If you go to RSN, click on the template. So you will get pipe diagram like this. You can select which one you want. For example, you want a micro and RF. So which solver it is suggesting, that is also one of the important thing, right? For example, if you go to optical application, go next. You want either plasmonic or metallic structures. If you're getting dielectric structures, go next. If you're designing the solar cell or optical waveguide or photonic band gap structure or filter resonators, or if you are selling filter resonator, which solver is best suited, it will be coming in the top. Frequency domain or time domain. Frequency domain. So we can select frequency domain. So similarly, it will suggest for each application the best solver is suited. You can use that solver or you can change that solver later also. It's not necessary you want to use the same solver, okay? Similarly, if you go for the antenna, there are different kind of antenna, 5G millimeter wave, or dielectric resonator, RFID, or phased array unicell, so mobile phone antenna, or waveguide antenna, okay? Or reflector antenna, just say go to reflector antenna, you will get the selection. Integral equation or time domain. So you can select integral equation, you can go next. Similarly, each application, it will suggest you the best suitable method. Okay. Now I will show you something with the okay. I will show you an antenna along with an amplifier circuit. Okay. So this is the basic graphical user interface of the CST, and you have all the modeling methods are here. It's very easy to design, model the things over here. Okay, all the standard options are there, bending tool, and you have a history also. So history is something like that. For example, I have created this component. I don't want this component. I can just delete it. I can update it. So this geometry will form along without that particular component. You don't need to press the control result for this much time. Just delete. For example, just you see that I will show you a small geometry I will create like this here. Okay. So if I create it, it will ask me to delete that thing. So if I delete it, then if I go here history, I can just select that particular thing and I can delete it and update it. History is one of the most easiest or most important thing. Now for every application we select, we will get all the list of solvers that support in that application. For antenna, all the 6 solvers are supporting. So different application for different kind of solvers. And also you have optimizer. That optimizer have different kind of optimization methodology like time to contrast region framework, Nethermead of CMA operation, evaluation strategy, genetic algorithm, particles optimization, interplay Quasi-Newton, Classic-Powell. So genetic algorithm and particle swarm are very important, right? You already know they are called as the global optimizers. So for every different solvers, you have different settings will be there. You can also have field monitors, voltage monitor, field pops. You also have different kind of excitation methods are there. Okay. So if you go to time domain solver also, you have a different kind of machine is there. You can change the accuracy here. You have so many options are there. And if you just select the I solver, instead of T solver, you can even use I solver. Then if you go into I solver, you can see that different kind of methods will be there. Right. Different kind of methods will be there. What are the methods? MLFM, ACA, MOM, enhanced MLFM. So different kind of methods will be there as well. Okay. So you can just understand which method is suitable. You can use the simulation accordingly. Now for this antenna, I want to add an amplifier. So this is the 2 ports are connected, right? I want to add an amplifier. Just click onto schematic. Schematic is nothing but the design studio. Now, what are the things you can design? Okay, if you are, you can connect this block to any other module in the CST. Or if you want to import any data, like you want to import a touchstone file, you want to import a SPICE network from somewhere else, you can import here. Or you can convert one mode to another mode. You can have mode converter here. And also you have a amplifier. You can add an amplifier, or you can add a directional coupler. You have an isolator. You have a power divider. you have attenuator, everything is there, block is there. And if you want to design something like a transmission line, coaxial line, coupled transmission lines, options are there. And if you go to microstrip, you have bends, different kind of bend structure, stubs, discontinuities, coupled line, coupler, anything. Just select and you set the width and depth and everything, it will work. Similarly, you can have a strip line as well. Similarly, you have a waveguide structures. So you have more options here, discontinuities, H-plane obstacles. Similarly for the circular structure as well. Then in circuit components, source and ports, or you can also see the diode here, and you have a MOSFET here, you have amplifier, operation amplifier here, right? Zener diode is a thyristor there, right? Or you can go in general, you have inductor, capacitor, all these things are switches, everything is here. And also you have a device model library. So from the device model library as well, you can get the different kind of components. For example, you want NB BJT transistor, you just click here. You can sell it to the manufacturer and you can use it, right? ST Microelectronics, you can use it here. So this is all about the design studio. And from here also you can do the analysis. You can do you just want to calculate the S parameter. Or if you want to calculate the AC combined result. If you select AC combined result, what you are getting is, if you enable the combination, whatever you simulate, it will reflect in your 3D model. Okay. Same way you can add amplifier, IBS, or if you want to add an array from here, you can do this array. If you want to add from optimization, you can add optimization. Okay. And here, what I have done is, I have selected the particular problem. I did the simulation. So I did the campaign here. So what I'm getting is, like you can see, is this amplifier is actually working in at 3 gigahertz. So this is the amplifier circuit, which is actually working in the 3 gigahertz. So when I did the simulation, so you can see here, when I did the simulation without the amplifier, it was 12,202 volt per meter. When I added that amplifier, you can see it is a very, very huge number. Okay. Again, will not be having any difference, but you will get the power will be different. So this is one of the things. Second thing is, for example, if you want to create an array thermal analysis of this one, you have thermal option. If you click the thermal option, you can directly go for the thermal analysis. Or if you just want to create an antenna array after this, you can click on the antenna array. So what will happen is, you will get option to create antenna array. So what are the kind of antenna array it support? You can give a diamond shaped antenna array, hexagon shaped antenna array, or octagon shaped antenna array. You have to just provide the value, it will create the array accordingly. Okay. So for that thing, I will show you an antenna array which I already designed and simulated to save the time. Okay. Okay, this is a very simple antenna. So here I have created the antenna array already. If you look at here, so this is a base element. From this base element, I have constructed the antenna array. Let me check. Yeah. So if you go to the excitation button, if you click on the excitation button, you also get the option for cosine, Taylor, binomial, Chebyshev, Gaussian, all the standard kind of excitation mechanism into there. You don't need to provide any value to the array. It will be automatically calculated on the area of your interest. So I have created like this, but here I am applying like uniform distribution, right? Here I am also interested in the grouping. So this is the same thing I was mentioning. I have 60 elements. and if I group it, group means every group have a mentor. So it will need to calculate only the group mentor, because that group mentor represents the effect of all the other elements. So instead of wasting your time in hours of simulation, you can just select the simulation of the group member. So similarly, this is 17 groups are there. I did the simulation, I got the result. Or if you didn't do it, then it will create the array for all the injured elements. Similarly, I have created a handler antenna array simulation. So here I have applied a Taylor series expansion. So you can see that the amplitude distribution, if you select a Taylor, so you already know that how the Taylor series are looking like, right? Now let's see the result. So if I'm going here, okay, this angular array, it will create automatically. You want to do anything manually, it will create according to the shape you're interested. So what you have seen is you can see the combined radiation pattern. It will come. Okay. If you go to the 3D pattern, you can see that the antenna array with having a 20 dB gain. So this is the radiation pattern. Now, if you want to scan it, I already did a scanning also. So you can see that -62 + 60, all the scanning is performed. So these are very simple. What you have to change is, so when you do the antenna array task, it will give you two variables. Using that variable, you can perform the antenna array scanning. Okay.
So
I will show you.
yeah, on to add on top of this, sir, like basically CST comes with the complete suite where you don't have to have individual add-ons for any of the things. So as a research pack, you get the entire module. So there is no limitations at all. So whatever Sumit is showing, so it is all part of the module.
So like you can see that this scanning is already performed around the 45-degree phi angle and the theta angle -60. So you have to just provide these variables here. So it will give you the scanning output. So these are the different method. I can also show you some other methods also. So this is about the antenna array, because we can sometimes later, if you are interested, we can even go for the all suite demo also. But
Yes.
I don't think that it's just like awareness kind of thing. Now I will show you another one, which is much complicated. So if you see, another one is yeah. No, the other thing is you can even yes. So another thing is you can even use a structure and you can add your antenna over that one, and you can do the simulation. So this is a kind of simulation we already did. So we placed an antenna array over here, right? Then this is the base station antenna. So you can see the base station antenna placed over here and did the simulation. So this is also possible. Like even in academic license, this one is also possible. You can even add a geometry and do the combined simulation. So basically, you are going to get the platform interaction, platform effect. Similarly, I can show you something of interest. So this is with a varactor. Generally, we configure antenna, right? One of the interesting point is there. So I have selected a varactor over here, pasted to this point, and I did the simulation. I can just show you the S parameter for the varactor. So when I change the values of the capacitance of varactor, so you can see that it will give me different kind of resonance. Similar thing, what you can do is you can go for the very hard modeling of this particular structure. So you can, I will show you something like that. The realistic model of how it actually looks like. So you can see that this is the complete pin diode. So this is the bias. Inside that one, your structure is there. So here your diode is actually placed. So this is a real one because where you want to add your bias capacitors and everything. And this is your schematic where you have added the equivalent of the particular diode. You can add like the property of a diode using the touch transfer, etc. And I will show you something more. Let me check.
Sumit,
Yeah,
Sumit, anything specific? Maybe we can show one or two because we are running out of time. So
yeah, we do it. So this is an RFID structure. So this is an RFID. This is one thing. So it have a far field response like this. So it will be like a omnidirectional pattern. Now, if you can also do the bending of this RFID is very simple. You can bend it. So this one is vacuum. This structure is vacuum, so it will not have any effect except the shape deformation. Then you have add a phantom. The phantom is like a hand model. So you can see this hand model, which is available, and you paste that RFID over the hand model. Two things you can see is you can see the radiations. Now you can see that there is a change in the radiation pattern, right? This change is due to the presence of the hand, right? And also what we can calculate is we can calculate the SAR. So SAR is something very high here. You change because there is nothing. There's a metallic structure. There is nothing to reflect it back, right? So it is a very free hand structure. So you will definitely have that effect will be there. Similarly, you can even if you, instead of this one, if you want to add a voxel data, you can even import a voxel data. Okay. So the voxel data will be having, like as I mentioned before, it have the parts of human body, like you say the Gustav model. So this will be free of cost. You will get this one by default. Because you say that you have a lot of research publication you are looking for, right? So you will get a human body with all the parts, and if you select it, you can change the property of that one. If it's currently 100 megahertz or 900 megahertz, there's an option here. From here, you can even change the material property, like a different material property. You can change that to a different frequency, so you will get a very accurate model.
So just to add on to this, sir, RVR College from your city, so they are using for a similar application, that is biomodule. So they extensively use this biomodule for their research and projects. So we had provided them during last year December the license. So this is just for your information, sir. Yeah. Sorry, Sumit, go ahead. Yeah.
So this is the one I was mentioning. So I created this RFID, this complete RFID structure I created using the blocks. Okay. So I selected the microstrip blocks. So I created through that. You can add this file and everything. So you don't need to manually design anything. You can just create it. You go to assembly. You can create it as a 3D project. Very simple. Okay, one more thing I want to show you, one last thing. I'll show you the realistic antenna array model. So this is a complete antenna array structure, including the box and everything. So this is the feeder network. This feeder network is completely designed here itself. Okay, and I will show you So this is the model, 3D model of that antenna array. I just removed the box just for doing this image. You will the same result. You can see that complete structure along with this feed. So this complete feed is designed here only. And this is the pattern, around 20 dB gain is there. But I'm not interested alone on not only that, I will be doing this simulation for the complete answers. So we can do the thermal simulation also. Whatever the power we applied, is just 0.5 watts something. So you can see this is the temperature. So Kelvin, which is the degree Celsius. So when this antenna is actually operating, you will have around 32.98 degrees Celsius. But here I just applied 0.5 watts of power. If I increase the power, you will have a more temperature present there. So if the temperature is there, I had to use any method like heating, or when I can simply add a fan to reduce the speed. So you have an example, you have option here, a fan. If you enable fan, then I will get a fan over here. I can use the flow thermal analysis and I can add and can reduce. So CST is like the package where you are not just limited to design the antenna, it's more than that. So that's the reason you can get a lot of publications in CST than any other. So anything else you want to see?
Sir, we are open for the questions. So if you do not have any questions, maybe we could conclude.
Nothing, sir. Actually, we are new to for this CST studio now, right?
Okay. Yes, sir. That's where I told Mr. Rajesh sir also. So there will be a training session also would be given. So once you have the license taken from us, so it's like a extensive support we would be giving. So last month Sumit had concluded the training to RVR College, and recently last month we had given license to SRM University also, Amaravati. So it's part of the package. So basically, the training would also be included.
Okay, sir.
Yeah.
I'm also very thank you, sir, for this giving this CST studio for demo. We are also think about this, and we are discuss with the management people and running the people. Then after we can discuss with you, sir.
Sure, sir. Yes. So meanwhile, we will share you the documents, whatever the Sumit had presented today, whichever we could share it with you. So that becomes a reference for you, sir, to just give a justification to your management also. So meanwhile, if you want any support or any help from us, you can always reach out to us, sir.
Okay. Thank you, sir. And can you please send a quotation also sent to Rajesh, sir? He handed to me. Okay.
Definitely, sir. So I will offline of this call. So I will discuss with you. So there are certain offers also running for this quarter.
Okay,
so maybe I can connect offline. So then discuss with you in detail, sir.
Okay. Thank you, sir.
So I
thank you, Srinivasan, sir.
Yeah. Thank you, sir. Yes.
Thank Sumit Pillai garu, you also thank you, sir, for this CST studio demo. And Srinivasan, sir, you're giving a good connectivity platform to our antenna side, and it will be really helpful to our students and our faculty also to learning. Whatever new technologies on 5G or 6G or any areas. And thank you, Srinivasan garu, and thank you, Sumit Pillai garu. Okay.
Yeah. So from our side also, from BIAS team, we would like to thank all the faculty members who had joined our call. So hope we have learned something new today. So I would say stay safe, stay home. So because we are going through a tough situation these days. So thank you very much, sir, for connecting, and thank you, Rajesh sir, for setting up the platform to everyone. So thank you very much.
Okay, thank you, sir.
Thank you, Sumit.
Thank you.